In this video, we're going to talk about including Dalton's law of partial pressures, vapor pressure, Henry's law, and barometers. What are they? What are they used for? How do they work? Let's get started. So Dalton's law of partial pressure states that the pressure of any individual gas in a mixture of gases is the same as it would be if it were the only gas in that container or in that environment. The presence of other gases doesn't change the behavior of any one gas. Take our atmosphere as an example. Our atmosphere is a mixture of gases. And I want you to remember this only because as a resident of the planet Earth, you should know what you're breathing. 79% of our atmosphere is nitrogen. About 20% of our atmosphere is oxygen, only 20%, despite the fact that we don't need nitrogen to live. It actually makes up the vast majority of our atmosphere. About 1% of our atmosphere is argon, and a fraction of a percent growing is carbon dioxide, about 0.03%. There are other trace gases in the lower atmosphere, the troposphere where we live on Earth, and there are some other gases that don't exist in the troposphere to any great extent up in the higher atmosphere, in the ionosphere and the stratosphere, like ozone, hydrogen oxide, sphere, as well as water vapor. But for the most part, this is mainly, those others are in parts per million, or parts per billion. These are the only ones that have any real significant presence in our atmosphere. So the partial pressure of a gas is simply the pressure of that gas. The gas pressure that would be there that you would measure, even if the gas were all by itself. Now, the sum of the partial pressures of all the gases in a mixture add up to the total pressure. So in other words, the whole is the sum of its parts. If you add up the pressure of the oxygen, nitrogen, argon, and carbon dioxide in our atmosphere, they'll add up to 1 atmosphere. They'll add up to 14.7 psi, or whatever atmospheric pressure is, whatever unit you want to use at sea level, or wherever you happen to be. So we designate this PT, where T stands for total. The total pressure equals the partial pressures. Partial pressure is indicated with a capital P and then sub A, B, C, where A and B and C just are stand-ins for whatever the identity of the gas is. So for example, the partial pressure of oxygen gas would be written capital P sub O2. Partial pressure of argon would be capital P subscript AR for argon, etc. So that's how you write that. So the total pressure is just the sum of the partial pressures, which makes perfect common sense. The sum of anything is when you add them all up, or the total of anything is its sum. In other words, gases don't behave differently when they are in a mixture with other gases. They behave just like themselves. Another way of putting this, and this is pretty much saying the same thing, but the partial pressure of any one gas in a mixture is equal to the mole fraction. The mole fraction, remember, is just the number of moles of one gas divided by the total number of moles of all the gases, including the one gas whose mole fraction you're calculating in that total. So the mole fraction is basically a percentage, but without the percent, it's a fraction without multiplying by 100. So what this is saying is that there's a directly linear, and not even linear, but an exact relationship between the number of particles of a gas, the sheer number of particles of a gas as a fraction, and the proportion of the total pressure of that gas out of the entire total pressure. The fraction of the total pressure is equivalent to the fraction of the moles of the gas out of the total number of moles of gas. So the mole fraction of a gas, say for example, gas A in a mixture of gases A, B, and C would be the number of, and this is designated by a Greek letter chi or chi if you prefer. It's not chi. It's not chi. Please don't pronounce it chi. It's chi. Maybe not that hard, but that's what it is. Moles of A divided by the sum of all the moles of gas, including the moles of A. Just like a percentage, you include in the denominator, you include the unit from the numerator as well as all the other units as well. Just don't multiply by 100. However, if you do multiply by 100, a lot of mole fractions, or instead of using mole fractions, oftentimes we're going to see that the percentage of a gas, the molar percentage, or even the volume percentage of a gas is going to be used as a perfectly valid substitute for mole fraction. So for example, up here, I have 20% of the atmosphere in terms of volume and in terms of pressure is oxygen. And that's perfectly fine to use. It means exactly the same thing as the mole fraction. All you have to do is convert your percentage to the equivalent decimal, and you have yourself a mole fraction. In other words, a percentage is the same thing as saying, oh, well, that's the same thing as saying 2 moles of A out of every 10 moles of gases, including A, 20% is 2 out of 10, or it's 20 out of 100 moles. Same thing, any fraction that gets you the exact same, wait, I don't think I did that right. 20 out of 100 is 0.2. 2 out of 10 or 20 out of 100, 200 out of 1,000, 0.2 out of 1, it doesn't matter. The point is any fraction that gets you to the same value, the same molar fraction, is perfectly valid and perfectly fine to use. So we're often just going to use percentages rather than raw mole fractions. But then you'll have to convert to the mole fraction by dividing by 100. That's all you do. So for example, the chi, the mole fraction of argon, is simply 0.01. Just take that 1%, and convert it into from percentage into a decimal by dividing the number 1 by 100. 1 divided by 100 equals 0.01. You plug that into your calculator, 1 divided by 100, that's the decimal your calculator will spit out. Now, here's the thing, gases in a mixture are under the same conditions of volume and temperature and total pressure. What this means is you don't have to worry about one gas having a different pressure and temperature from another gas. If they're in a mixture, almost by definition, they have to be under the same conditions of pressure and temperature. How can you have a mixture where one gas is experiencing a different temperature than the rest of the gases around it? It doesn't make any sense. It's like being in a car, but you're hot, you're feeling air of 60 degrees while the driver is experiencing air of 100 degrees. That doesn't usually happen, unless there's something wrong with the heating or air conditioning. Okay, gases don't have that problem. So their volume fractions are the same as their mole fractions. So the volume to volume ratio of one gas to the total number of gases, or like say, for example, the V volume of A to the volume total is exactly the same or equivalent. The ratio is exactly equivalent to the moles of A to the total moles, which is of course equal to the pressure of A divided by the pressure of T, the total pressure under the pressure of A, the partial pressure of A. So you can depend on that because the pressure and temperature have to be the same. Let's take a look at an example. And while we're looking through this example, we'll talk about some other, kind of real life factoids for you as well. I'm going to go deep sea diving. This is already fiction. I've never gone deep sea diving, nor do I intend to. All right, I'm going deep sea diving down to 80 meters below the surface, but 80 meters max. This is a true fact. Every 10 meters below the surface adds 1 atmosphere of pressure to the amount of pressure you are experiencing above and beyond the air pressure you would experience above the surface of water. Every 10 meters below the surface, add 1 more atmosphere. So at 10 meters below the surface of the water, you are experiencing 2 atmospheres. 1 atmosphere from the air that you had already been experiencing, plus an additional atmosphere of water pressure pressing up against your lungs. This can get dangerous very quickly as you descend into the deep. Okay, so going 80 meters down means you're getting 80 meters divided by 10 meters equals 8 atmospheres plus the 1 atmosphere you were already experiencing above the surface of the water, for a total of 9 atmospheres. So you are experiencing a total of 9 atmospheres of pressure on your lungs, on the outside of your lungs, pushing you in, squeezing you like a giant squeezing you, like you, just a giant squeezing you. But it's the water squeezing you. So I need to fill a breathing tank with gases at a total pressure, PT, of 9 atmospheres. Now here's the problem. I can't just shove 9 atmospheres of oxygen into a breathing tank. I need to, first of all, why do I need 9 atmospheres? Because if I don't have an equal amount of pressure on the inside of my lungs pushing outward, if I don't have an equal amount of pressure on my lungs pushing outward, all that pressure from the outside again, is going to squeeze my lungs completely closed or nearly completely closed. The pressure from the water outside will squeeze my lungs down into this. I can't have that. So I need an equal amount of pressure pushing back against the water pressure. In other words, if I have only 1 atmosphere of pressure, the amount of pressure that I would normally breathe in at above the surface of the water, that's not going to be enough to fight the water pressure that's squeezing me like an empty tin can. 9 beats 1. So we don't want that. So you have to fill your lungs with enough pressure so that they can push back against the water. But the problem is you can't just fill the tank with oxygen, because oxygen in too high of a partial pressure is actually toxic for you. Remember, oxygen is a highly reactive gas. It makes things burn. And if you've ever heard of the idea about antioxidants fighting off all those oxygen-free radicals in your body, now I'm not entirely convinced about that, but the idea is there is some basis for the idea that oxygen does do harm to your tissue as well. Too much oxygen is reactive. It'll basically burn your lungs from the inside if you've got too high of a concentration of oxygen in your air. So 9 atmospheres is too much. So you'll suffer from oxygen toxicity, which is a real thing. Now, there's also a problem. Now, nitrogen is a relatively inert gas. So nitrogen doesn't really react with any of your tissue, your body's tissues. However, nitrogen has its own problems. It's a di molecule. It's a diatom, which we haven't talked about yet. Okay. Oh yeah, we have. Yes, we have. What am I talking about? Yes, we have talked about. So we know nitrogen is diatomic. It's 2 nitrogen atoms bonded together. What does this mean for us? It's a relatively large molecule, and even though it can fit through some of the pores or the openings in your cellular membranes, the fact is if it leaves your blood and your cells too quickly, it will cause damage on the way out. And that's the problem. You saturate your tissues and your blood with nitrogen. When you come back out to the surface, you're going to experience sort of the reverse of Henry's law, which we'll talk about later in this video. All the nitrogen is going to basically boil away, not because of high temperature. I don't want you to think boiling is because of the high temperature, but it's going to boil away out of your blood and out of your tissues so fast it will cause damage on the way out. So you can't use nitrogen, you can't use oxygen at too high of a pressure. What you need to do is you need to fill your gas tank with some inert gas that's not going to do any damage. Introducing helium. Helium is a great gas because not only is it inert, because it's not reactive because it's a noble gas, but it's tiny. Helium is so tiny that it'll easily pass right through your body without getting trapped or doing any damage on the way out. Helium actually floats through rocks. It's one of the reasons why we have a helium shortage on this planet right now. Helium goes right through the rocks and right out of the atmosphere. It's hard to capture. It's being generated constantly, but it's also flowing through all the cracks and crevices in rock. That's how small it is. So if you can do that, it can get through your body as well with doing minimal amount of damage. So it's tiny enough that it doesn't hurt you on the way out. And that's really what you need. So for that reason, Heliox is a mixture of helium and oxygen. It's 95% by volume helium and 5% oxygen. But remember, 95% by volume implies 95% by moles as well. Under the same conditions of pressure and temperature and volume, your mole ratio and your volume ratio is the same, pressure, temperature, and moles. Obviously, volume is not going to be the same, but in other words, the volume, let me rewrite that. The mole ratio of helium to the mole ratio of oxygen, remember, helium and oxygen are both related to PV over RT. Well, if the pressure is the same for both, and R is the same because that's a constant, the temperature is the same, well, what do we have? Well, then that implies that the mole ratio of helium to oxygen is exactly the same as the volume ratio of helium to oxygen. So they're the same ratio. What that means is that 95% by volume is the same thing as saying 95% by moles. So we can trust that this is okay to use in our partial pressure relationships, in our partial pressure expressions. Okay, let's get rid of all these lungs. Freaking me out. So the question is, or question A is, if I used regular air, now forgetting about the Heliox mixture for a moment, what if we thought, hey, I breathe air at the surface. What's wrong with breathing air underwater, just under higher pressure? Okay, I understand that I need the higher pressure. So I'll pump in a lot of regular air into my gas tank, into my breathing gas tank, I mean, not my car. I'll pump in a bunch of air, I'll put it under high pressure, because I understand the need for that. I should be fine, because 20% oxygen is good at 1 atmosphere. Why shouldn't it be good at 9 atmospheres? So if I use regular air, but pressurized to 9 atmospheres in the tank, what would the partial pressure of oxygen, in other words, the PO2, P sub O2 be? So P sub O2 is going to equal what? Well, let's convert, so regular air, remember, is 20%. Remember back over here. Regular air is 20% oxygen by volume, by moles, whatever you want to say. We're going to interpret that as moles. It's 20%, so that's 0.2. Its mole fraction is 0.20 mole fraction. We can use a percent as mole fraction because they're basically saying the same thing. Even if it's by volume, assuming you have the same pressure and temperature, volume ratios and volume fractions are the same as mole fractions. So my partial pressure of oxygen is just going to be my mole fraction of oxygen multiplied by the total pressure. In this case, we're setting the total pressure to 9 atmospheres. So what do we get? Well, we get 0.2 times 9. That's 1.8 atmospheres of oxygen. Oxygen toxicity begins at 1.2 atmospheres. Partial pressure begins at a partial pressure of oxygen of 1.2 atmospheres. This is exceeded that by 50%. This is 50% above the toxic level, the minimum toxic level. You go in with this, you're going to get sick and possibly die. So you don't want to do that. So instead, what you're going to want to do is use some other gas mixture that contains mostly inert helium. So take the 1.2 as a sort of guideline. It's sort of an average of different activity levels. All right, 1.2 m. So this is way too high. This is dangerously high. Dangerous. Of course, you don't want to suffer from hypoxia, which is too little oxygen. Okay, so what is my partial pressure of oxygen in the heliox tank? Now, in the heliox tank, the partial pressure of O2 is what? Well, it's going to be, you're still going to have 9 atmospheres, but your mole fraction is 5%. Well, 5%, remember, 5% divided by 100 is 0.05. So our mole fraction of oxygen, which is our percentage converted to a decimal, is 0.05. That's our chi value for O2 in the heliox tank, multiplied by a total pressure. Again, it's still 9 atmospheres, though. So 0.05 times 9 is going to be 0.45 atmospheres. Still higher than atmospheric partial pressure of oxygen, but in the safe zone. You haven't exceeded any kind of threshold for oxygen toxicity. So you have more than enough oxygen, but you're not at toxic levels, and you have enough pressure coming from your tank to expand your lungs against all the force pushing or squeezing your lungs shut. Okay, let's take a look at another example. I have a mixture of gases that I made by combining 0.85 grams of fluorine and 1.2 grams of carbon dioxide. If these gases are stored in a 6-liter tank at 7 degrees Celsius, what are their respective partial pressures in PSI? Okay, let's take a look. So partial pressure. So I want to find out the partial pressure of fluorine gas, and I want to find out the partial pressure of dry ice, carbon dioxide. Let me rewrite this a little bit more nicely. Partial pressure of carbon dioxide equals what? So we know it's going to equal the mole fraction multiplied by total pressure. So what are our mole fractions? Let's calculate the mole fractions of each one. The mole fraction of fluorine is going to equal what? Well, it's going to equal the moles of fluorine gas divided by the moles of fluorine gas plus the moles of CO2, dry ice. Dry ice turned into a gas, of course, not in its solid form. Okay, so it looks like we're going to have to figure out the moles of both of these. So let's do that. Let's do that over here. So we have moles, 0.85 grams of fluorine. We know that every 38 grams of fluorine. Now, how do we know that? Because it's 19 grams per mole for fluorine, but we have 2 of them. So that's going to be 2 times 19. If you look at the periodic table, you'll see that fluorine has an atomic mass of 19. Times 2 is 38. So 38 grams of fluorine for every 1 mole of fluorine. So that gives us 0.85 divided by 38. That's going to give us 0.02237. And since I'm right at the beginning of my calculation, I'm just going to go ahead and not round very much. I mean, I'll give myself a few decimals. So that's moles of fluorine. That's not our mole ratio, that's just moles. Then we take our 1.2 grams of carbon dioxide. We know that it's 44 grams of carbon dioxide for every 1 mole. Again, the molar mass or molecular weight comes from adding up carbon, which is 12, and 2 oxygens, which is 32. That adds up to 44 grams per mole. So we take our 1.2 divided by 44. That's going to be 0.02727 moles of CO2. Okay, so to calculate the mole ratio for each of these, mole ratio of CO2, mole ratio of F2, that's going to be, so for fluorine, we have 0.02237 moles of fluorine divided by 0.02237 plus 0.02727. So we add these, we take this mole fraction here. So this time, unfortunately, we don't have a percentage given to us. That's too bad. Starting to appreciate that percentage. 0.02237. Hopefully I'm number crunching correctly. I get 0.4506. That's my mole fraction for fluorine. Then I do the same kind of calculation for carbon dioxide. This time it's going to be my 0.02727 divided by 0.02727 plus 0.02237. No percentage, right? I'm not trying to put a percentage here. So that's going to equal, let me just separate these. Let's see, 0.02727 divided by 0.027, parentheses, divided by parentheses 0.02727 plus 0.022. This is one of the few times when I actually feel like I need to use parentheses rather than, because I can't do this any other way. I can't like divide because these are being added together. I can't simply say this divide by this divide by that. That does not work. I'm adding now, not multiplying on the bottom. So I have to use the parentheses in my calculation. And if I can draw a round decimal, that would be even better. Okay. That gives me 0.549. That's enough. 0.549. Okay, 0.5494. Let's just round up. So those are my mole fractions. Now the question is, what I want to know, that's the mole fraction, but I need to multiply those by the total pressure. It's just one problem. I don't know what my total pressure is. Now there are two ways to go about this. And frankly, I'm not sure which one. They're both kind of number crunchy and kind of tedious, but you can do it one of two ways. Either you can take each one of these moles or mole fractions, or actually you could have just taken each mole, plugged it into its own ideal gas equation, and figured out the partial pressure that way. Or you can take the total number of moles of both of these together. In other words, take this number right here, this total, either one, by the way, they're both the same. Plug it into the ideal gas law along with the volume and the temperature. Plug it into the ideal gas law, get a total pressure, and then multiply each of that total pressure by each one of these mole fractions. Personally, I'm not even sure which one's the better option. Just because this is the partial pressure Dalton's law example, I'm going to go with the latter option, but you can try it as a way to double check your work. Try it the other way. Take each one of these moles over here and plug them into the ideal gas law separately, each one, and see if you get the same answer. That's one way to double check your work, is to do it in two different ways. They should give you the same result because you're basically doing the same kind of math. Okay, so my total number of moles, N, is going to equal the sum of both of my moles. So 0.02237 moles plus 2727 moles. My total moles for the total pressure of the gas is going to equal, well, let's see, 0.02237 plus 0.02727, 0.04964, 0.04964. That's my total number of moles, that's my N. So if I want to solve for pressure, total pressure, PT, is going to equal the pressure from all of the moles of gas. In other words, both of these moles of gas. So PT is going to equal my N value, N times R times T divided by V, which is going to equal 0.04964 moles That's both of them put together, times 0.0821 multiplied by our temperature, which is 280 Kelvin. You know by now to use Kelvin, add 273 to this, that's 280. Divide by our volume, which is 6 liters. Thankfully, it's in the unit we need instead of having to convert. So we're gonna get our units in atmospheres, which is, oh, I wanted PSI. 0.0, well, that's okay. For now, 0.04964 moles multiplied by 0.0821 multiplied by 280 kelvins divided by 6 gets me to 0.190 atmospheres. Okay, that's the total. Since we're already here, let's just go ahead and convert to PSIs. We know that every 1 atmosphere is 14.7 PSIs. So that's going to equal 2.8. I'm just going to write 2.8. That's easy enough. 2.80 PSIs. For once, PSIs are actually an easier number. That's our total pressure. Remember, that's our PT, total pressure. So how do we figure out the partial pressures? Just multiply their total pressure by each one's fraction. Actually, you only have to do it once. Here, let's take a look. I'm going to erase all this stuff over here. We already know how we figured out all the moles. If not, you can always rewind. Be kind, rewind. Okay, let's erase all this. I wish I had a bigger eraser here. Okay, so let's figure out the partial pressure of fluorine. Partial pressure of fluorine is going to equal our mole fraction of fluorine, which was 0.4506. And just in case you have trouble seeing that on the page, that's right over here. That's right over here. 0.4506 multiplied by our PT of 2.8 PSI. And so that equals 1.26 PSI. Now here's the thing. So that's our PF2, that's part of our answer right now. We can do the other one, we can figure out the PO2 in one of 2 ways. We know that these are the only 2 gases. So technically 2.8 PSI minus 1.26, don't worry about the sig figs right now, let's just get this problem, is going to be 50.56. It's going to be 1.56 PSI. That's going to be our partial pressure of oxygen gas. We know they have to add up to the total pressure. Therefore, if I simply subtract fluorine's partial pressure from the total pressure, I should get oxygen's partial pressure. But let's double check ourselves and see if our math is correct. So double check. PO2 should equal, we should get 1.56 by also by multiplying 0.02, oh no, I'm sorry. Why am I saying O2? CO2. We can get our CO2 by multiplying, and again, in case you're having trouble spotting all these numbers, 0.5494, that's our mole fraction, 0.5494, multiplied again by our total pressure of 2.8 PSI. Hopefully that gets us something around 1.56, you know, within rounding at least, right? 0.5494 times 2.8, 1.54, close enough. There's probably a little bit of rounding affecting us here. 1.54 PSI. Close enough. You know, you can double check your numbers. You can maybe check your roundings, whatever. It's most likely right. I did a little bit of rounding in the 2.8 PSI, although that shouldn't have 0.4506, 0.5494. It's close enough for me. So either one of these methods should get you there. So if you calculate one partial pressure, simple subtraction should get you the other one. And then the other way to corroborate this and to double check your work is to, instead of even going through the whole partial pressure thing, is just plug each one of these moles that we calculated earlier into its own individual ideal gas law to see if the pressure each one of these pressures pops out. So you can calculate the ideal gas law. So for the pressure of fluorine equals moles of fluorine, RT divided by V, and then moles of carbon dioxide equals N moles of carbon dioxide, RT over V. Now the R, the T, and the V are all exactly the same. And so you could do that. Okay. I'll leave that to you. Give that a try. See if you come up with the same answers. You should. It should come out to be exactly the same thing because it is, at the end of the day, the exact same math. Let's look at another example. I have a 40-liter tank of helium at a temperature of 27 Celsius and kept at a pressure of 50 psi. I then pump 6 moles of oxygen into the tank, assuming the temperature isn't allowed to increase. This is kind of a hypothetical example because if I don't allow the volume to increase and I don't allow the temperature to increase, let's see, what are the partial pressures? Oh, so I should be pumping up the pressure. That's what I'm saying. Okay, that's good. All right. So the pressure is building up. Assuming the temperature isn't allowed to increase, what are the partial pressures of the helium and the oxygen in the tank? Volume can't change. This is a tank after all. Okay. So pressure will go up, but we don't know what the final pressure will be. So I have a 40-liter tank of helium. So let's write all this down. Volume equals 40, well actually there is no volume one, it is volume, that's all it is. 40 liters, volume equals 40 liters. Temperature equals 300 Kelvin. 273 plus 27 is 300 Kelvin. Pressure is 50 psi's. So that's at the beginning. I pump 6 moles of oxygen into the tank. So at the beginning, all I have is helium. I have enough here to figure out the moles of helium. PV divided by RT is going to equal pressure, of course we have to convert, so 14.7 psi's per atmosphere. So 50 divided by 14.7 is going to be about 3.40 atmospheres. So we have 3.40, this is just for the helium before we've added anything else. Our volume is 40 liters. Our temperature is 300 kelvins. And of course, we have our gas law constant is always constant, 0.0821. So that gives us 3.4 times 40 divided by 0.0821, divide again by 300. That gives us 5.52 moles of helium. So our moles of helium is 5.52 moles. Then I pump in 6 moles of oxygen into the tank. So now I have a total of 11.52 moles in my tank. Assuming the temperature isn't allowed to increase, what are the partial pressures of the helium, the oxygen in the tank? Okay, well, let's see. I've now got mole I can calculate my mole fractions, but what is my pressure? Well, my pressure can't possibly be 50 psi anymore or 3.4 atmospheres anymore, right? Because now that since I didn't let volume change, pressure must have increased because I pumped more moles of gas in there, but I didn't allow any expansion of the tank. So what's my new pressure? In effect, we kind of have Avogadro's law here, don't we? But we have a version of Avogadro's law where we're relating pressure and moles instead of volume and moles. We add more moles, but we don't allow the volume to change. So technically, the pressure and the moles are directly, well, they're holding volume constant. Pressure should increase as you increase more moles. So what I'm going to do instead is I'm going to calculate the new pressure, P equals N RT over V. But here, this time, my N value is going to be 5.52 plus the 6 moles that I added. So it's going to be this total here of 11.52 moles times 0.0821 times the same temperature, because I didn't let the temperature change, 300 kelvins, and I didn't allow the volume to change, so that's still, where's my volume? Oh, here it is, 40 liters. I had a hard time finding that. Okay, 40 liters. So we have 5.52 plus 6, that's 11.52 times 0.0821 times 300 Kelvin divided by 40 liters, 7.10 atmospheres. So and that makes sense because we've almost doubled the number of moles. Without changing the volume, our pressure should just about double. And it did, actually it more than doubled because we added more than 5.52 moles. So we more than doubled our pressure. So what is the partial pressure of each one of these? Well, we just take our partial pressure, our mole fraction. So we take our partial pressure of, well, since helium came first, let's say the helium. Partial pressure of helium is going to equal our mole fraction of helium, which is 5.52 moles of helium, divided by what? Divided by 11.52. Our total moles, now that we have oxygen in the tank, our total number of moles is no longer just the 5.52. It was 100%, right? It was a mole fraction of 1. Now it's a mole fraction of, looks like a little bit under half or about half, no, a little under half moles O2 plus helium. And so that equals, well, let's take a look, 5.52, multiplied by our total pressure, which is 7.1 atmosphere. I'm afraid after all of this, we're probably going to end up with exactly what we expect. It's going to be a very intuitive answer, which is not bad. It just kind of makes you wonder why you did all this calculating. 3.4 atmospheres, but that's okay because part of this is to confirm our common sense. Not a coincidence that we ended up with exactly the same number. Why? Because what did I start off this section by saying? The partial pressure of a gas is the pressure of the gas as if it were all alone in a container, whether it's in a mixture or not. Even if a gas is in a mixture of gases, its partial pressure is exactly the same as if it were alone. Here we literally can see helium, when it was all alone, had a pressure of 3.4 atmospheres. Now that it's part of a mixture with oxygen, it's still exactly the same, 3.4 atmospheres. So the remainder then, the partial pressure of the oxygen must be 7.1 minus 3.4, which is going to be 3.7 atmospheres. But let's double check our number anyway. So partial pressure of oxygen, let's take our mole fraction of oxygen, which is 6 divided by 11.52. Let's just double check these numbers, make sure they come up to be the same thing. So we take our mole fraction of oxygen multiplied by the total pressure, and we should come up to exactly the same thing. 6 divided by 11.52 multiplied by 7.1, the total pressure, and we get 3.697, which is rounded up to 3.7 atmospheres. So we get it either way. they agree, which they should agree, whether you subtract from the total. If you only have two gases, or just subtract one from the total and you get the other one. If you have more than two gases, well, then add up all but one of them and subtract them from the total. You should come up with the one that you didn't add or you didn't calculate. So this kind of confirms already what I said earlier, which is that you get the exact same partial pressure of a gas, whether it's alone in the tank or whether it's part of a mixture. Now, of course, the other part is the oxygen. We wouldn't have known what its partial pressure was until we calculated this. And of course, there are always alternative ways to do this. For example, you could have just said, okay, well, partial pressure of oxygen should just equal the, you could have just gone straight to the ideal gas law. Partial pressure of oxygen is N, 6 moles, times 0.0821 times temperature of 300 Kelvin divided by 40 liters. And that would have given you, this should also give you 3.7. Let's see if it does. 6 times 300 is 1800 divided by 40 is going to be 450, if I'm not mistaken, 445 times 0.0821, 3.6945, or rounds up to about, pretty close to 7, 3.69 atmospheres. So yeah, any one of these methods could have gotten you the same answer. I just kind of went the long roundabout way because I wanted to do another example with Dalton's law of partial pressure. Most of the time you don't even need it because it's such common sense. Any one of the other laws will actually help you. As long as you understand what's going on, you can actually take a lot of shortcuts in these laws if you understand what's going on. If you don't, then you're kind of locked into whichever method most matches what you see in front of you as far as variables and what you can think of first. Okay, let's continue on. Let's talk about barometers. A barometer is just a tool to measure atmospheric pressure, regardless of where you are. It doesn't have to be at sea level, doesn't have to be anywhere on Earth even. So barometers work like this. Most barometers involve a little pool of mercury, liquid metal. And I'll explain in a moment why it's mercury and not something else. Actually, you can already read it. If you can read this, if you're reading the side here, you can already see what the reason is. Mercury is a relatively dense liquid. For that reason, it doesn't take much of a height of mercury to add up to a significant weight. Because there's so much density, this little bit of height, 76 centimeters or 760 millimeters, remember 76 centimeters is 760 millimeters of mercury. This is where we get that unit, 760 millimeters of mercury being 1 atmosphere. It's from this, 29.9 inches if you're an American. Okay, so the idea here is that air pressure exerts a force downward on the surface of the mercury. So this surface of the mercury is supposedly exposed to air pressure. However, not content to just stay there. Remember, there's air pressure pushing down, but liquids and air is a kind of a liquid in a sense, push in all directions. So if there's a pressure being pushed downward, there's also a pressure being pushed upward. So the liquid gets pushed upward here. Now you might say, well, usually if you place a straw into a drink, you don't notice this, right? And not only do you not notice it, it's because you don't notice it because it doesn't happen in a drink. I have no idea if this is the right way to draw it. Okay, anyway. All right, so that's the idea. You have a drink here, but usually when you stick a straw into a drink, the level of liquid inside the straw stays right about the same level as the drink outside. It doesn't pop up. It doesn't just shoot up into your mouth unless you suck it up into your mouth. You're not going to get any, right? So why does this barometer work this way? Why does the liquid mercury in a barometer shoot up? Well, it has nothing to do with the mercury. Any liquid would do the same thing, including water. The difference between a barometer and a cup with a straw in it is that there is no vacuum. Until you supply the vacuum, there is no vacuum at the other end of the straw, so the water stays at its own level. However, there is vacuum at the very top of the mercury tube. There is no gas pressure at all. In other words, though there's an air pressure pushing down, which in effect pushes up, there is no force pushing down, pushing back down against the flow. There is no force going this way, or at least no air force, right? There is one force, however. The only force that there exists is not the gas force, because there is no gas there, but instead it is the sheer weight of mercury. It is the gravitational force. So I should say, I'm going to amend my statement here. There is no air force or no air pressure, force divided by area, which is pressure, pushing back. However, there is gravitational force. The sheer weight of the mercury is pushing downwards at a force equal to the mass times g, the acceleration toward the center of the Earth, 9.8 meters per second squared. In fact, there's a term for this that you can relate pressure by rho g h, the density of the material, the liquid, multiplied by the gravitational acceleration that we all experience, times the height of the column of liquid, which is measured from the base of the liquid to the very top of the liquid. And at sea level, that's going to be, well, we already see it, 760 millimeters or 76 centimeters or 29 inches, depending on whatever units you want to use to measure that. So there is a force, but it's the gravitational force that keeps the mercury from rising indefinitely. In everyday life, however, you don't have that. All you have is air pushing back against the liquid inside of a cup. Until you put your mouth on there, I'm not going to draw that. Until you put your mouth there and create a vacuum with your cheeks, or however, or through your lungs, you're not actually applying any vacuum. So the water isn't, or the liquid in that cup is not going to move. But there's always a continuous vacuum here. In the absence of a force, air force will push this liquid up. Now, if you were to drill a hole into this top point here, open this up, air would immediately flow in, and this liquid level would drop right down to its surface, because all liquids seek their own level. All liquids seek their own level. It's said about water, but it's actually true about all liquids. Seek their own level. What that means is no liquid wants to rise above its fellow liquid molecules, or liquid particles, I should say, except in the absence of any kind of contravening force under the action of another force pushing in a single direction. Now you might wonder, well, why do we use mercury, which is a known toxin, instead of using, say, something like water? Well, remember, part of the pressure, part of the force, the gravitational force pushing down and keeping this liquid mercury column from just rising forever into the sky, is the fact that mercury has some sort of weight. It has density. It has a certain amount of mass being pulled down by the Earth's gravitational pull. Mercury's density is 13.5 grams per cubic centimeter, or per milliliter. That's the rho, or the density of mercury. The rho, or the density of water, is 1 gram per cubic centimeter. What does that mean? That means that the mercury is much heavier. Therefore, the force of the air is only able to lift the mercury about 76 centimeters. Water, being 13.5 times lighter than mercury, meaning less dense than mercury, would shoot up about, not even 30, about 34 feet into the air. Because water is so much lighter, it's much easier for the air to push water around and push it right up that tube. And so a barometer based on water would have to be about 34 feet high. It would be about more than 3 stories high. And I don't know about you, but I don't have anywhere to put a 34-foot high barometer. I can't even get a Christmas tree into my place of decent size, let alone a 34-foot barometer. So because of that, we don't use water. We use the toxic liquid metal mercury instead. Of course, there are electronic ways to do this nowadays. And you can also use other kinds of devices which use a difference in height of liquid across sort of separating the liquid from one side to another. Those are usually made with alcohol with some sort of food coloring inside of them, if you've ever seen them before. Anyway, there's lots of ways to measure them. There's also a manometer, which just is sort of like how the one I'm describing now. I don't really have a picture of one right now, but it's kind of like a circular tube it's sort of an S-shaped tube that goes up and then goes down. It sort of looks like, you're actually going to see a picture that's sort of like it in a moment. Sort of looks like this, and then the manometer goes down and up like this. And then you measure, you measure it based on the difference in height of the liquid being pushed around inside the manometer, which is this curvy tube, and you measure height difference like that, and that's how you get it. Anyway, so that's the idea behind barometer. It's basically air pushing against a vacuum and seeing how high a column of liquid, whether it's mercury or water or some other liquid, can get. So the air is literally pushing up against nothing. That's why it's able to go. Only gravity prevents it from going even higher. Let's talk about a concept called vapor pressure, and also let's relate that to boiling point. Vapor pressure is actually the pressure of the gas phase of a liquid when it's in equilibrium with its liquid above the liquid in a sealed container. That's a lot. Okay, so let's break that down a little bit. So one thing I wanted to mention here, and this is related to vapor pressure, it's not completely true that the top of the barometer tube is pure vacuum. There is no pure vacuum anywhere. There's always a little bit of pressure, but in this case, there is some of what's called mercury vapor, meaning just a really, really low level of mercury atoms that have escaped from the liquid phase because of the ambient thermal energy in our world, because of a little bit of heat everywhere, or the heat everywhere, some of the mercury has vaporized, we're talking extremely tiny quantities, by the way, and become a sort of, it is exerting a little bit of gas pressure because it's vaporized gas. So the mercury, there's a tiny, tiny bit of mercury vapor pressure. By the way, another problem with using water as your barometer, water has a significant vapor pressure at room temperature, about 20 millimeters of mercury. Now, while you could correct for that, it is something to consider. That water does it at different temperatures. Your water-based barometer will actually have different errors and will need to be recalibrated for every different temperature, because at every different temperature, water has a different vapor pressure. Meaning at higher temperatures, you're gonna have more water vapor pressure filling what's supposed to be vacuum and pushing the liquid water down your barometer. That's another reason why you shouldn't use water in a barometer. It's got too high of a vapor pressure. Mercury, on the other hand, is liquid metal, so it takes extremely high temperatures to get any significant kind of vapor pressure out of a metal. Metals have very strong interparticle attractive forces. They don't like to let go of each other. Okay, so what does it mean to have vapor pressure? All liquids exist in an equilibrium between the liquid phase and the gas phase. All liquids, even mercury, which is probably the least likely candidate to have such a dynamic going on. When I say equilibrium, any equilibrium in general means a condition where you have two opposite processes occurring simultaneously at equal rates. Oftentimes we use, to reflect this, we use what are called double half arrows like this to show that a process is going in both directions at the same time, from left to right and from right to left. Chemical reactions can do this too. They actually go from reactants to products and from products to reactants in reverse. Reversible reactions establish an equilibrium. So an equilibrium is a process, is a set of processes, a pair of processes that are diametrically opposed to one another, doing opposite things simultaneously at the same rate, so that there is no apparent change in any quantity of on either side. Meaning, if it's a reaction, you don't get any change of products or change in reactants, but products are continually being converted into reactants, and reactants are continuously being converted into products. Likewise, when it comes to liquids and their vapors, and a vapor is nothing more than the gas phase of a liquid in the vicinity of that liquid. When it comes to liquids and vapors, they exist in an equilibrium where liquid molecules are constantly being vaporized to form more gas phase molecules or gas phase particles. But simultaneously, those gas phase particles are coalescing. They're bumping into each other, coalescing, liquefying, and bumping into the surface of the liquid and getting reincorporated into the liquid again. So you have, like 10 molecules on one part of the liquid becoming vaporized, and somewhere else you have 10 different vapor molecules coalescing or coagulating and becoming liquid again. So they're happening at the same rate. So these two opposite processes are resulting in no net change, despite the fact that both processes are happening continuously. It's kind of like, imagine you and someone else are outside in a field. You're digging a hole. So you're sticking a shovel in and pulling dirt out of the ground and throwing it into a pile elsewhere. But at the same time, someone else is going to that same pile with their shovel and shoveling that dirt right back into the hole that you're digging, back and forth, both of you working at the same rate. Every shovel you shovel out, he shovels back in. And you do this all day long for eternity. That's what equilibrium is like. Lots of action, no changes. Kind of like Congress. Okay, so that's what equilibrium is all about. And that's what's going on. So vapor pressure builds up when you seal a container that contains a liquid with a little bit of room above the liquid so that you can build up vapor pressure. If you leave a container open, all the vaporized former liquid molecules are allowed to escape, and they go off into the universe and they never come back again. So there's no equilibrium allowed to be established. The gas particles are no longer present in order to be reincorporated into the liquid. So it would be sort of like in the example of you digging a hole. If you dug a hole and then every time you took a shovel of dirt out of the ground, you took that dirt and threw it away so far away that the other person couldn't shovel it back into the hole. That would be different. Then you couldn't establish an equilibrium. You would end up digging the hole deeper and deeper and deeper. Likewise, without a seal over your container of liquid, eventually all the particles evaporate, they vaporize, evaporate away, and you're left with no liquid left in the container. I'm describing all this. I have a picture on the very next page. It might be easier for you to look at this picture while I'm talking about it. So vapor pressure and equilibrium. Why didn't I have this up before? Okay, so this is kind of how to imagine it. You have your liquid level right here. As long as you have just enough liquid to create enough vapor without completely emptying your container of all liquids, you can establish an equilibrium. And the other requirement is that you have a sealed lid on top. Now, if the lid is open, what happens to those vaporized particles? Well, eventually they go out into the world, never to return ever again. Never to return. And by the way, the concept of equilibrium is so critical to chemistry and to biology too. A liquid sitting for a length of time in an open container evaporates. It evaporates and never comes back. It never returns. All these particles are not going to reliquefy because the container is open. So no stable, significant pressure or vapor pressure will ever be able to build up. Vapor pressure very much depends on having a seal over your container, having the gas, the vaporized liquid particles as a gas, having them trapped. They need to be trapped. If they're not trapped, no vapor pressure ever builds up, and you have no vapor. You essentially have no vapor pressure. I mean, you might have a slight increase, but it's not measurable or worthwhile. But as soon as you tamp down on this, all those particles are now free to bounce around. And as they do, some of them will eventually bounce back into the liquid and get reincorporated. Some will bounce into each other and coalesce and liquefy. So some of them will get reincorporated just by directly contacting the liquid and getting reabsorbed into the liquid as liquid particles. Some will coalesce in midair and form sort of droplets inside of the container and fall back down into the liquid phase. But at the same time, others will rise back out again. And both of these processes will occur at the exact same time. So as some fall, others rise. And that's the cycle of life. So that's equilibrium. The same processes occurring at the same, processes that are exactly opposed to one another occurring at the same time at the same rate. And in order for vapor pressure to build up, you must seal the top of that liquid container. But there has to be enough room for gas to develop. If it's completely filled up with liquid, then obviously you're not going to get any vapor. It's all going to remain in the liquid phase. By the way, this manometer here, manometer is like what I was describing just earlier, a few minutes ago, a little bit earlier. That's a device for measuring the pressure, the air pressure in any kind of tank. So for example, this manometer measures the buildup of pressure of this vapor here, the vapor pressure, by measuring the difference in height. Here you have air coming in. So air pushes down on one side, but the pressure over here pushes back on the other side. Depending on the relative heights on this side and inside, where this column of liquid, by the way, this liquid is not the liquid from inside here. This is some other liquid. It could be mercury, alcohol, something else. It is not, this is not the overflow. This is not an overflow. This is not the liquid from inside the container. This is the liquid, this is some other liquid that is built into the manometer. So depending on where the relative heights are for the manometer, that's how you know what the relative air pressure, the relative pressure is of the inside of this container, the vapor pressure compared to the air pressure. So it's this difference in height. You don't measure all the way to the bottom. You measure from surface to surface. That's your equilibrium vapor pressure. That's your vapor pressure. You don't really measure vapor pressure until you reach equilibrium. You would not measure vapor pressure in of an open container. It simply makes no sense because there is no vapor pressure being established. So that's the idea behind vapor pressure. All liquids generate a certain amount of gas particles because those liquids have a tendency to vaporize, but they also have an equal tendency to reliquefy. Now, what happens if so much of the vapor gets generated that you not only generate a small vapor pressure, so for example, water, at about room temperature, about 20 degrees Celsius, water generates about 20 millimeters of mercury of vapor pressure. 20 millimeters of mercury is nothing, right? 760 is air pressure. We're talking about 20 out of 760. That's not even 1%. Hold on, is it? Hold on, let me 2 divided by 76 times 100. Okay, my apology. It's 2.6%. That's 2.6% of air pressure. That's nothing. That's hardly any pressure at all. At 20 degrees Celsius, there's a small but significant vapor pressure for water. But keep raising that temperature, 30 degrees, 40 degrees, etc. Keep going until you get to 100 degrees Celsius. Then what's water's vapor pressure? Then water's vapor pressure becomes 760 millimeters of mercury, or in other words, 1 atmosphere. That's what we call the boiling point. The boiling point is simply a special case of vapor pressure. The boiling point, the general boiling point, is defined as the point, the temperature at which a liquid's vapor pressure, the vapor pressure equals the local, wherever you happen to be, the local atmospheric pressure, wherever you are. Now, of course, if you're at sea level, then you have the standard or the normal boiling point, which is the temperature at which your vapor pressure is 1 atmosphere. But not everybody lives at sea level. Not everyone is so lucky. If you live in the Mile High City, or if you live in a very high location, like a place like 7,000 feet up at the top of a mountain, for example, or a mountain community, you'll notice that your water boils at much less than 100 degrees Celsius. That's because for you, you don't have the normal boiling point, which is defined as the temperature at which the vapor pressure equals specifically 1 atmosphere. For you, you have a boiling point where your water boils maybe at 90 degrees Celsius. Why? Because your local atmospheric pressure maybe is 0.9 atmospheres because you live so high up. You are at such high altitude that your air pressure is lower. Remember, the higher up you go, up a mountain or up anything, up in high altitude, air pressure goes down. So if you live really high up, your air pressure, your local air pressure might be 0.85 atmospheres, which means your water, your vapor pressure of the water, your water is going to match that at a much lower temperature. As temperature increases, the vapor pressure of any liquid also grows, meaning you generate more particles, more of the liquid particles become vapor particles. The equilibrium gets shifted toward making more vapor instead of more liquid as you go higher in temperature. Well, if you're at if you're at a lower atmospheric pressure, then you don't have to reach as high of a temperature for your liquid to generate as much vapor pressure as your lower local atmospheric pressure. So it's easier to achieve boiling at high altitudes because of the lower vapor pressure, the lower atmospheric pressure. That's the idea. So boiling point is the temperature at which vapor pressure equals local atmospheric pressure. And I know I already have this written down in the previous slide. That's boiling point. The normal, and this is an official term, I'm not just saying, I'm not just being judgmental. The normal boiling point is equal to the temperature at which any liquid reaches a vapor pressure of exactly 1 atmosphere, or 760 millimeters of mercury, or 14.7 psi, or whatever the equivalent unit you want to use is, etc. Those are all the same thing, right? They're all the same. 1 atmosphere, 760 millimeters of mercury, 760 torr, 14.7 psi, 101,325 pascals, 0.987 bar, whatever unit you want to use. They all mean the same thing. So the normal boiling point, and in case you don't want to read my terrible handwriting, the normal boiling point is set to 1 atmosphere. So the normal boiling point of water is 100 degrees Celsius, whether it boils or not where you live. It's not dependent on where you are. However, the general definition of boiling point of a liquid is the temperature at which its vapor pressure is equal to the surrounding atmospheric pressure. So if you are on Mars, for example, the boiling point of water would be something very, very cold. Water would probably boil at room temperature or colder because the atmosphere on Mars is about 1/6 of what it is here. So 1/6 of 760, let's see, 1/6 of 760 is 12.6 millimeters of mercury. 12.6 millimeters of mercury. Well, at around 10 degrees Celsius or so, water has this as its vapor pressure, or the partial pressure of H2O. So water would probably boil around 10 degrees Celsius on the surface of Mercury, which probably explains why there's virtually no water on Mercury unless it's frozen. Because, actually even frozen water can also vaporize. We'll talk about that a little bit later though. So, yeah, it just depends on where you are. So I think I'm right about that. I'll have to double check the actual air pressure. It might be even lower than that on Mars. I don't know, I don't remember. It's been a while since I've been there. I'm kidding. All right. Okay, I said everything on here, everything else here. Said that the vapor pressure of a liquid is the partial pressure exerted by the liquid's gas phase. That's another way to say it, in case that helps. By the way, we call water in its gas phase, we call it steam. We don't usually have names for other types of liquids in their gas phase. We just call them gas, but water gets special names for its different phases: ice, water, steam. Okay. So let's talk a little bit about some other properties of gases. Henry's law states that the greater the partial pressure of a gas, not the vapor. Okay, now I want to make a distinction here because I run the risk talking about this right after I just talked about vapor pressure of a liquid. You might think I'm still talking about the liquid itself. I'm not. The vapor of, not the vapor of the liquid, but a different gas altogether. And we'll talk about, I've talked about this a little bit before when I talk about carbonating a carbonated beverage or carbonating something. When you shove carbon dioxide into a liquid to make a sparkling beverage, a bubbly beverage, you are putting carbon dioxide, you're putting a high pressure of carbon dioxide into the water. How? By increasing the partial pressure of carbon dioxide gas above the water. And again, I have some nice pictures here. The greater the partial pressure above the liquid, the greater the concentration of the gas inside the liquid. And I think that's pretty much common sense. Gas particles move wherever they can move. The liquid air surface is not much of a barrier to a gas. It will simply enter a liquid just as it will enter another empty space. So this is how beverages get carbonated. In normal atmospheric terms, carbon dioxide occupies only about 0.03% of our atmosphere. But if you have all your carbon dioxide pressurized, so you can put 1 atmosphere of partial pressure of carbon dioxide above a liquid, a lot more carbon dioxide will enter that liquid. And then if you quickly seal that container, you've got yourself a nice bubbly Coca-Cola or Perrier or I don't know, whatever drink you drink that has bubbles inside of it. Oh, this also works for nitro coffees and nitro teas. Those are just nitrogen gas instead of carbon dioxide gas. They put nitrogen inside and they put it under high pressure, even higher pressure than atmospheric pressure. And you just put a bunch of nitrogen air bubbles. Likewise with foam or whipped cream, you're just shoving a bunch of air into liquid particles. That's all it is. One other thing, this is not necessarily related to Henry's law, but I just thought I'd mention this here. At higher temperatures, all gases become less soluble in liquids. Now, regardless of the partial pressure above the liquid, if you increase the temperature of a gas, the gas particles get excited, they move around a lot, and they expand. As they expand, less of them, as long as there's room for them to leave the liquid state or to leave the liquid, they will expand outward, and you'll see less gas particles per cubic volume, unit volume, and that means there will be fewer of them in the water as well as fewer gas particles in the air above the water. So as you raise temperature, you have fewer gas particles for every unit volume, which includes fewer gas particles per unit volume of liquid. They basically move out of the liquid. This is a problem on Earth. There are so-called dead zones, sometimes caused by warming oceans and warming lakes, because the higher temperature results in less oxygen dissolved in the water, or I should say just inhabiting the water, or we'll say dissolved, but technically it's not dissolved. Less gas, less oxygen gas dissolved in the water. Aquatic life suffers when the temperature of water increases. That's because there's less gas, there's less oxygen in the water, and maybe it reaches a critical threshold where there isn't enough oxygen to support life. The life forms die in that section of the ocean. Usually these sections can be huge, the size of cities or states. So it's not like the creature can just swim elsewhere to where there's more oxygen. It might be kind of far and they might run out of oxygen before they can get anywhere. Anyway, that's the idea. So this isn't really Henry's law, but I just thought I'd mention that right here as well. This is another concept related to the solubility of gases in liquids. Henry's law specifically states the greater the partial pressure of an unrelated gas above a liquid, the more of that gas you will find dissolved in the liquid. And I have some more little pretty pictures here. So this is just Henry's law visualized. So at one bar, which is just above atmospheric pressure, you have a certain amount of these gas particles dissolved inside the water. If you double that, if you double the partial pressure above the liquid, guess what? We had 3 gas particles here, and now we have 1, 2, 3. Now we have 3 new gas particles. We have a total of 6 gas particles. We double the pressure above the liquid. Therefore, we double the soluble gas particles inside the liquid. You know, take that with a grain of salt, but the idea is the same. The higher the pressure above the liquid, the greater the concentration of gas particles dissolved within the liquid. Of course, this takes some time. And by the way, other than you can do, this is one way. This shows just the natural pressure of the gas increasing above the surface of the liquid because there's twice as many gas particles. Of course, that's not the only way to increase partial pressure, right? The other way to increase partial pressure is to what? Well, to compress. Compression can also result in higher pressure. Compression results in higher pressure. You decrease the volume. Compression is a decrease in volume. Expansion is an increase in volume, right? That's what we've been talking about all this time. Compression, expansion. Expansion, you increase the volume of a gas. Compression, you decrease the volume of a gas. So you can raise the pressure. You can raise the pressure through compression, Boyle's law, right? If you decrease the volume, you increase the pressure. So that's another way. You don't put more gas particles in the world above the surface of the liquid. You simply compress the gas particles above the liquid. In fact, you could do this for carbonation. The reason there are 3 pictures here is you're at equilibrium beforehand, then you suddenly compress, give it some time, and eventually you reach equilibrium. Equilibrium always takes a little bit of time. Give it some time before you know for sure that you're in equilibrium. Once you're in equilibrium, you get all the gas particles that are going to dissolved, and then you're there. And of course, there's a back and forth. At equilibrium, you have both up. You have, again, as always, you have some particles leaving the liquid and some particles entering the liquid. And again, this is not vapor pressure. This is just a foreign gas, quote unquote, foreign gas entering the liquid and being dissolved in the liquid. This is not part of the liquid's own gas phase. This is a separate foreign gas entering the liquid, just like oxygen in water, not steam or water vapor in water, oxygen in water, carbon dioxide in water, nitrogen in water. This is what we're talking about. We're talking about Henry's law. We're talking about foreign gas particles dissolving in another liquid. Let me go back here a little bit. I just wanted to represent this a little bit here. So the way you'd represent this with those arrows I showed you earlier, those double pointing or left and right pointing arrows. So one way you could represent this is you can represent, let's say this is water down here. What's going on here is you have water in its liquid state, and once it's reached equilibrium, you have water in the liquid state and water in the gas state moving back and forth. At equilibrium, both of these arrows are exactly the same length because both of these processes are happening at the same time. A sudden change might cause a shift in equilibrium where you, for just a short period of time, you might have a quick out of balance disequilibrium representation. Sometimes the relative lengths of these equilibrium arrows are used to show something that is out of equilibrium, at least for a short time. But then again, it's also sometimes used to show that maybe equilibrium or maybe equilibrium favors the gas state. For example, at higher temperatures, at high temp, equilibrium will produce a lot more gas and a lot less liquid. So this can either an imbalance here can either represent a disequilibrium, or it can represent the relative favoring of equilibrium for one side over the other, for one state over the other. So those are I just wanted to represent, that's how you represent equilibrium chemistry, mainly through the equilibrium arrows. And sometimes you can use those arrows creatively to say a little bit more, either about the equilibrium or to express even that maybe you're in disequilibrium, but usually more often to show that equilibrium favors one side over the other. Okay, that is the gases. That's just about everything I had to say about gases. I don't think there's anything left. After this comes the next section, so we'll talk about that in the next video. I hope all of this made sense. I hope you enjoyed that. Please let me know any questions or comments. Let me know if you have any concerns or if you want to talk about any of this. I'm all ears. Hope this was helpful. I'll see you in the next video. Take care, everyone.